Let's start with the concept. The topic which I am going to discuss is EMF induced in rotating rod. When it is rotated in uniform magnetic field. So this is the concept we are going to understand now. Let us assume a rod which is pivoted, which is going to be pivoted to a region. So this is pivoted here. Now this rod is rotating within constant velocity, that's called angular velocity omega, and now this is going to be the path taken by the rod. Now in this entire region there will be uniform magnetic field is acting. So now we have to calculate what is going to be the induced EMF in this rod. First we need to understand, does it induces the EMF? So if you ask that question, yes, it will induces the EMF in the rod. Basically, EMF when the rod moves in the magnetic field induces because EMF formula is BVL, where magnetic field is going to be, if you imagine, B is going to be the magnetic field which is acting inward direction, and velocity of the rod. So you just imagine, if it is rotating with an angular velocity omega, means every point on the rod will be having different linear velocities. Why? Because we know that V is equal to omega into R. This is the relation. That means at each point of R, that means from here to here, so from here to here, every point there will be separate distance will be there, different distance will be there. So each distance will contribute different velocities. Okay, so magnetic field though here constant, everywhere in this region magnetic field will be constant, but velocity at each point of the rod is having different value. And the length though, so length also from here to here, each point length is going to be different, but even though you can imagine from the center to here the length will be remain same. So if you take here, the length is going to be, the length of the rod is going to be L. So now we are going to calculate. So what's going to be we are calculating, because of this velocity, because of the presence of velocity at each point. So now we are going to calculate what is going to be the induced EMF in that point. So to do that, see, let us consider a small length element. Let us call dx is the small length element. In this dx, so we are going to find out what is the induced EMF. This is the dx length, so very small length. In this dx length at a particular instant of time, so this is having a linear velocity in this direction. This is the linear velocity direction. At a certain instant of time, you can observe the linear velocity will be at that instant will be in this direction. So omega though in this direction only, in the anti-clockwise direction, velocity will be for this dx element. So for this dx element, So we can write it as it is going to be having a linear velocity of v. Now, so this is having the velocity and it is having a thickness of dx, and it is having it is in the magnetic field. That means it will be induces some EMF. That what is that EMF induces? We can easily use the palm rule. By the palm rule we can say, so if you apply the palm rule, what will happen? So let us take, this is going to be the palm. If you apply, so now what is going to be the velocity? The thumb will represent the velocity direction, and the remaining fingers will represent the magnetic field. So then here we can easily say that, so the magnetic field is inward direction and the velocity is going to be represented by the thumb. That means all the negative charges will be settled on, so if you take, this is going to be the direction, all the negative charges will be settled on the, so this side, this is the side where negative charges will be settled. All the negative charges will be settled here and the positive charges will be settled here. So that means it will be act like a, we can say, a very small dx length will be act like a very small battery like this. So it will be a positive terminal and this will be a negative terminal. So now here this is going to be the EMF induced in this, we will call it as dE. So now what we will do, we will find out what is going to be the total EMF induced. How do you calculate the total EMF induced? So first we will write for the dx element what is going to be the EMF induced. So before going to that dx element, so let us take from the center where we pivoted to the point where we are finding the EMF is having a distance x. Now we will write an equation. So the induced EMF in the dx can be written as, so we can write it as dE is equal to, so magnetic field will be remain same. So magnetic field will be remain same. We will write B, and V is nothing but, V can be written as omega into R. R is nothing but here, R is nothing but here X. So then we can write it as omega into X, and we got the V is equal to omega into X. So next we are going to take the length element. What is going to be the length element where we are finding the induced EMF in a small dx length? That means we have to take dx. So now what we have to do? So now we have to integrate this, because from year to year, why we are integrating means each point are having the different velocities. If you say here, if you calculate the velocity value is going to be bit more than this is v dash, and if you calculate here it's going to be further more velocity, and like that if you go near to the center the velocity is decreasing. That means if you go on away from the center the velocity is going to be increasing. So then velocity is increasing means it is an understood that the induced EMF is also going to be increases, because it is directly related to the velocity. Induced EMF is directly related to the velocity. Now what we will do, we will integrate this. So while integrating we have to apply the limits from where to where. If you assume that this is going to be the center and this is going to be the length L, from center to the length L, from center to the length L. So let us call this is the center to here, it is going to be having the length L. Now for this length, that means we can apply the limits. So here 0 to L. So this is going to be the integration limits. Now integration of dE will give you induced EMF, total induced EMF, and integration of b omega x dx will be, b will be constant, omega will be constant, and then integration of x dx will be giving you x square divided by 2. Now apply the limits 0 to L. So then if you apply the limits, we can write it as b omega L square divided by 2. So that means of b omega L square. This is the formula for induced EMF. So this is the formula for induced EMF in the rotating rod. So that means the complete rod, if you take the diagram again, so the complete rod will be, so this is going to be a rod, means the complete rod will be act like an EMF source. EMF source means we can write it as, so this will be completely act like a EMF source, means this will be the positive terminal and this will be the negative terminal. Like this, it will be act like an EMF source or a cell. So now what is going to be this? This is a positive terminal, and this is a positive terminal, and this is going to be a negative terminal. Positive terminal and negative terminal. So now what will happen? If this is going to be the positive terminal and negative terminal, so now this is going to be the induced EMF case. So if you measure across this with a galvanometer, if that is rotating, if you measure with a galvanometer, the galvanometer definitely shows if any connection is there between these two ends, means the current will flow in this direction. So this is what, when it is rotating in the magnetic field, it is can be identified by connecting the galvanometer. So now what we will do? So we will just do with a more number of rods, not one rod. So if you do with more number of rods, let us take, if we include more number of rods, so let us take, there were n number of rods in the ring. So let us assume this is a ring. The ring is having, so let us take some rods are there. So let us call, these are all the number of rods. There were n number of rods, but I will take, so there are n number of rods or spokes are there, so which are going to be rotated at this pivoted point with an angular velocity omega. Now what will happen? Each rod, let us take the radius of the each rod is going to be capital R. When they are rotating with an angular velocity omega and the radius is going to be capital R, now each rod will be act like a cell, an individual cell. That means each rod will induce some EMF. That induced EMF we can calculate as, so let us take, this is going to be the induced EMF by this cell, by this rod. So then induced EMF in this is going to be, again we can write it as like this. In this we can write it as induced EMF as like this, and in this we can write it as induced EMF as like this. In this we can write it as induced EMF will be like this. And you have to understand that this is going to be a rod. This is a rod, and this is going to be the center of the this, wherever it is going to be rotating. All these are going to be, you can imagine as a rods or a spokes, which are going to be connected to the center from the wheel. Now you can observe here. So when it is going to be in the uniform magnetic field, if they are rotating, means what will happen? So if they are rotating, means they are having the angular velocity omega. So they are having the angular velocity omega. That means definitely they will induce us the EMF. The induced EMF by a single rod, if you take, so then what we can write? So we can write it as, so off into the induced EMF from a single rod, we can write it as, so E is equal to off into B omega. What is the length here? Length of the rod is going to be, whatever the radius is there, the same radius is going to be the length of the rod. So that means off into B into omega into R square, where R is the length of the rod. Now what we will do? So after understanding this, see, one single rod we got. So single rod induced EMF is going to be off into B omega R square. Now we have to find out what is the induced EMF from all these rods. So you just observe, this is going to be connected to the, all the rods are connected to the center, and the remaining part of the rod is going to be connected to the circumference of this wire, or we can write it as a circular loop. So that means all the connections are like this. So this is going to be one cell, and this is going to be another cell, and this is going to be one more cell. So like that, n number of cells are connected with this. So now if you are calculating between these terminals what is the induced EMF means, it is an understood that the first cell, the first rod, and the second rod, third rod, all are going to be in the parallel combination. When they are in the parallel combination, we know that induced EMF can be written as, so it is going to be the just an EMF of a single cell. So that means here you may have any number of spokes. Irrespective of the number of spokes, the induced EMF will be equal to half into B omega R square. So R square. So this is going to be the induced EMF. If it is going to be n number of spokes are there also, so the induced EMF will be considered for a single rod only. Why? Because all are going to be in the parallel combination. We know that parallel combination means, so each one whatever the EMF produces, so will be, or if they are producing it a equal amount of EMF, means it is an easy to find out the induced EMF, net induced EMF is also going to be equal to a single rod EMF. That is going to be what we are going to write here, E is equal to half into B omega R square. So you just take, let them give in the question any number of rods, so like this, like this, like this, any number of rods. So then if they ask the question what is the induced EMF in A, in this entire number of n number of spokes are also there, means you have to write it is going to be E is equal to half into B omega R square, where B is going to be the magnetic field acting and omega is going to be the angular velocity and R is going to be the radius of the spoke. Okay, so this you have to consider. This is going to be the induced EMF. So next, after this, once we understood this, so now we are going to discuss one more question. You can consider this as a question, or it can be an example or a case. So now we are going to consider a disk. A disk is rotating with an angular velocity omega. So now this is rotating with an angular velocity omega, means now let us assume that the magnetic field is acting inward direction to this disk. Now if they ask, let us assume this is the radius R and it is having an angular velocity omega and the magnetic field is going to be B. Now if they ask the question what is the induced EMF in the disk, what is the induced EMF in the disk, you can easily answer, because the disk is made up of infinite number of rods. Infinite number of rods. We cannot say any number because it is made up of infinite number of rods like this. That means if it is made up of infinite number of rods, means you can easily understand that all are going to be in the parallel combination. Each rods are going to be in the parallel combination. If they are in parallel combination, means the induced EMF is going to be, we can easily say, half into B omega R square. So the same induced EMF will be we are getting in the case of disk, but in the center we have to know that it is going to be a positive terminal, and the ring, that means on the circumference of this ring or a side on the edge of this disk, so we can say it is going to be having the negative potential. So the center is having positive potential and the edge is having the negative potential. So if you measure the potential difference, definitely the current will flow from if you connect any resistors across this, so you can say within another color I will show. So for example, if you connect, so from ear to ear, if you connect from ear to ear, the center of the disk to the edge of the disk, if you connect, now you can easily say from ear to ear it is going to be having the, this is going to be the deflection, because the deflection shows that current will be flowing from ear to ear if it is going to be a resistor is included here. So this is what the direction of the current flowing in the disk. Okay, so now let us consider one more question. Suppose this is a magnetic field. This is a question. In the magnetic field, a semicircular, so we can say a semicircular, the wire is going to be like this, it is made and it is pivoted here, and now if it is rotating with an angular velocity omega, if it is rotating with an angular velocity omega and the radius is going to be r, if it is going to be rotating with an angular velocity omega, what is the induced EMF in this rod or in this wire? If you ask, for this question you want to answer means, so you have to imagine this is going to be one rod, this is going to be another rod, and you have to remember the length here is whatever is there. We should not consider this entire length, we have to consider the vector length. Vector length means this also we have to consider in this point, only in this which is passing through the pivoted point. That means here R and here also R is there. So now in this point it is pivoted and it is rotating here. Now this is R means we just need to know that any number of rods are there. Any number of rods are there means also, so the induced EMF will be for single rod how much it is there, the same amount of induced EMF will be induces in this setup also. That means, so in this rod we can easily say the induced EMF will be equal to half into B omega R square. So B omega R square, where B is the magnetic field here. Okay, so the same expression. So you just need not to worry about this and you can easily answer this question. So next, after this, let's take one more example. A conducting wire is connected to a thread. A conducting wire is connected to a thread. Let us take 2L is the length of this thread and L is going to be the length of the conductor. This is a conductor and this is going to be the thread, and it is rotating with an angular velocity omega, which is rotating with an angular velocity omega, and the magnetic field, uniform magnetic field, is acting. Uniform magnetic field is acting. In the uniform magnetic field, the conducting rod of length L, which is connected to a thread, is rotating with an angular velocity omega. The magnetic field, we will write it as capital B. Now question is, find the induced EMF in the rod. How to calculate? So basically, when it is connected to a thread, definitely in the thread there is no induced EMF. Only this part of the conductor will induces the EMF. Now first we will calculate, assume that this thread is made up of a conductor, we imagine, and then we calculate what is the induced EMF from this total length we will calculate, and then we will remove this part of the, that means wherever the thread part will be there, that induced EMF we are going to remove this, and then we will get to know what is the total induced EMF. The reason for this is because each point are having different velocities. So if you consider here, that means, so the velocities are not going to be same as here. So that means when we are doing this type of questions, we have to do within total EMF we have to calculate, because this entire setup is rotating in this omega velocity, angular velocity. That means we have to consider this part of the rod. Means first we calculate total EMF induced by this entire setup, assuming it is a rod, and then we will calculate only EMF induced by this part, and then we will remove this part of the induced EMF. So in this total induced EMF, so let us do that. So let us imagine this is made up of completely a single conductor. So let us take, this is going to be a single conductor, and total length is going to be how much? So 3L is going to be the total length. Now induced EMF we have to calculate. Induced EMF is going to be what? So half into B into omega into total length is going to be how much? 3L whole square is there. So then we can write it as half into B into omega 9L square. This is going to be the induced EMF. Now we are going to take only this part from here to here. So let us take another rod which is going to be having a length of 2L. So for this we are going to find out the induced EMF. What is the induced EMF? Half into B into omega 2L whole square. It can be written as half into B omega 4L square. This is the induced EMF if it is going to be a rod in this 2L length element. Now what we have to do? We have to calculate the induced EMF in this rod. Now what we have to do? We have to subtract. So subtract this by this. Now net EMF is going to be in the rod L means, so we can write it as half into B omega 9L square minus half into B omega L 4L square. So then we can write it as half into B omega 9 minus 4 will give you 5L square. So this is the answer. The induced EMF in the length L of the rod is going to be half into B omega 5L square. So then if you just take L and if you answered, what you will get? Half into B omega L square you will get. That is not the correct answer because velocity is not same in every point. We just considered in the previous case this equation which we are calculated. It is for the velocity from the center we considered and calculated. So that's why we have to consider the total length and then calculate the EMF, and then we have to calculate from the center only. Everything we have to consider from the center to this point we calculate and then we will subtract. Here is the problem. So this is the way you have to follow. So next we will start with new concept, self-inductance. Self-inductance. Let us take heading self-inductance. What is self-inductance? First we will understand. First with a statement we will start. Self-inductance. The statement says self-induction is the property of a coil. Property of a coil or circuit. Property of a coil or circuit by which a change in current through it induces an EMF in the same coil that opposes the change in current. What is the meaning of this? So let us take within a coil. Coil means here I am going to consider the solenoid. So let us consider a solenoid. This is a solenoid. In the solenoid, what will happen? Suppose if you supply a current I, what will happen? This will induce us the magnetic field. The induced magnetic field will be so like this. So this is the direction of the induced magnetic field. So this is the induced magnetic field direction in this if the current flow is I is flowing. When the current I is flowing, the induced magnetic field is going to be magnetic field will be produced in the coil. Now the magnetic field will be, let us take, this is the direction of magnetic field. Now magnetic field will be produced in the coil. Now this magnetic field definitely will interact with this coil only. So that means when it interact with this coil, definitely some area will be there. So that means magnetic field will be in this direction and the area vector will be in the same direction. This is the magnetic field direction and the area vector direction. So if you take that, so then definitely there will be a flux which is going to be linked with this coil. That means even though the magnetic field produced by this coil only, but that can link with the same coil. So that means definitely there will be a magnetic flux which is going to be linking with this coil. Now what will happen? In the second case, I am going to apply a time varying magnetic field. What is time varying magnetic field means? With respect to the time, the strength of the magnetic field is going to be increases or decreases. Anything can happen. So but for the sake of simplicity, I am going to consider if the current is increasing. What is going to happen if the current is increasing means, now the current is increasing means what will happen? Definitely the magnetic field produced in this coil also increases. Magnetic field, if current is increases, definitely the magnetic field produced will be increases. When the magnetic field increases means definitely the flux which is linking to this coil, which coil? This coil will also increases. That means now the flux will becomes as a function of time, it is varying, because current is varying as a function of time. Now the magnetic field is varying with as a function of time. Now definitely the flux is also varying with respect to the function of time. So that means this varying flux which is linking into this coil will induces the EMF in opposite direction of the current supplied. This is the current supply direction, right? So to this opposite, and another current will be induces because of the change in magnetic flux which is produced by whom? Produced by the own magnetic field. That is what the statement is saying. Self-induction is the property of the coil or circuit by which change in current through it induces an EMF in the same coil. So that means if you take, this is going to be a simple version if you want to take. So this is the current flowing direction where I is the function of time is varying means definitely the magnetic field is also varying. When the magnetic field is varying means what will happen? It will induce us another EMF which is going to be opposite direction current is flowing. That means initially this is going to be the positive terminal and negative terminal, but what will happen here? It is going to be induces a potential which is going to be opposite to this direction. So why it is going to be induces means according to the Lenz's law, when changing flux is there means because d phi is varying with respect to dt means definitely there should be an induced EMF, but the induced EMF will be opposite to the direction of the whatever the EMF is supplied. That means this is going to be the induced EMF. For example, if you take this will be positive terminal and this is a negative terminal means time varying current if you apply it. So now what will happen? The induced EMF will be induces the current, so which is going to be, so like this, it's going to be in the opposite direction. That means you can take, this is the positive terminal and this is the negative terminal. Now current is flowing in this in the opposite direction. This is the induced current. This is not a normal current, this is the induced current. This is the induced current. I dash is going to be the induced current. That is what they are saying. So the same magnetic field produced, the magnetic field produced by the same coil will responsible for the magnetic flux in the coil, and that flux is changing with respect to the time. That same flux will induces the EMF in the coil. So this is going to be called self-induction. Clearly understand this. Self-induction means it's a property of the coil or circuit by which change in current through it induces an EMF in the same coil. It will be having in the same coil that opposes the change in current. That means whatever the current flowing will be there, that change it will oppose us. That means in the opposite direction the current will induce us. So this is going to be called change in means current it want to change itself. That means here whatever the external current we supplied, that current it don't want to increase here. So that is what it is doing. Induced current will resist the change. So when there is no change means there is no induced EMF, but there is a change in current with respect to the time means definitely the induced current will be there in the opposite direction. That will opposes the change of current, external current. Okay, this is called self-induction. So now we are going to further discuss related to the self-induction. So further discussion will be, so let us assume what is going to be the self-induction in a coil or a solenoid. So let us assume there is a solenoid. In the solenoid, I am supplying a constant current. Now, constant current is supplied means current is, assume that this is having a cross-section area A, and the magnetic field produced by this is going to be B, and then we are going to take flux is going to be linked with this coil is going to be phi. Now if I supply a current, first case it's going to be, we can take it as case 1. In the case 1, what I am considering is I is constant. I is constant. If I is constant, so then what we have to do? So I is constant means we can say that whatever the current is flowing in the coil, whatever the current is flowing in the coil, for the current flowing, so it will induce us the magnetic field. So definitely whatever the current is flowing, that will induce us the magnetic field in the coil. So that means current I, whatever you supply, for that proportional the magnetic field will be produces. The magnetic field, if it is producing means definitely there will be a flux. There will be a flux. That means easily we can say, so this flux is going to be nothing but the magnetic field which is linking to the same coil, which is produces the magnetic field. For that coil only the flux is the magnetic field is linking. So now what we can write, I is proportional to phi. We can write I is proportional to phi. So that means whatever the current is there, proportional to that the flux is going to be linking to this coil. Now what we have to do is, so we have to write to remove this proportionality constant. So then we will include IL is equal to phi, where L is going to be called as, L is called self inductance coefficient, where L is called self inductance coefficient. Okay, so now we can say L can be written as L is equal to, we can say L is equal to L is equal to 5 divided by I. This is going to be the self-inductance coefficient. So very important, this is a constant. So most of the questions will be asking, find the self-inductance coefficient for a given solenoid. So they may ask this type of questions. Now let us see how to find out the self-inductance coefficient for, see, this is going to be the self-inductance coefficient can be calculated by flux linked to the coil divided by the current flowing in the conductor or solenoid. Okay, so now we will see, this is going to be the case first to get the self-inductance coefficient. Now we can easily say what is the unit also. The unit can be written as, so we can write it as unit as flux is having the unit Weber per ampere. We can say Weber per ampere. Flux is a Weber, and inductance, self-inductance unit is going to be Weber per ampere also we can take. So we can write many units, many type of unit, many way we can write. So let us take, this is going to be having a unit of Weber per ampere. Now let us move on to the case 2. So in the case 2, what I will do, I just apply a time varying current. Now I will apply time varying current. That means I is varying with respect to the time. Now I is varying with respect to the time means what we have to do is, so we know that time varying means di by dt is varying. So that means we can say, so directly first we will start with I is going to be proportional to the magnetic flux. Now we can write it as, so I is varying with respect to time, means we can write di by dt and d phi by dt. That means current is varying with respect to time, means definitely the flux linked with this also varying with respect to the time. Now, so here so now what will happens, di by dt is going to be proportional to d phi by dt. So to remove this proportionality constant, I just introduce a di by dt. So L will be there and it is equal to d phi by dt. Okay, so now what will happen here, d phi by dt means what? D phi by dt means we know that induced EMF in the same coil, which is going to be opposes the current flowing. So that means induced EMF is equal to, so opposes means we have to consider opposite sign. So that means we can write L into minus L into di by dt. This is going to be the induced EMF. This is going to be the induced EMF. Okay, so this is going to be the induced EMF. Now once we got the induced EMF, now unit also we can write again. So L can be written as, another way of writing, volt time is seconds divided by ampere. This is going to be the another unit of self-inductance, another unit of self-inductance. Okay, so now we will calculate what is the self-inductance value for a solenoid. So let us take, so you can imagine it is a question also. So take a question like, a solenoid is having n number of turns and the flux linking is going to be phi and the cross section area is going to be a, and then the length of the solenoid is going to be L, and the I is going to be varying as a function of time. Now we have to calculate magnetic field is going to be B produced by this conductor or a coil. Now we will calculate what is going to be the induced EMF on, or before going to the induced EMF, you know that E is equal to minus L di by dt is the induced EMF. Now we have to calculate what is going to be the L value we have to calculate. To calculate the L value, we know that L is equal to phi divided by I. Now what is going to be the flux linked with this coil? It is nothing but B into A, N will be there, number of turns will be there, N number of turns. Now we can say BAN divided by I. So now this is going to be the flux and this is going to be the current. Now B can be written as what? So solenoid magnetic field can be written as magnetic field in the solenoid can be written as mu naught N into I. So mu naught N into I can be written as mu naught N I capital N here. So here it is going to be the magnetic field which is producing will be the N. So it's going to be it is going to be linking with the N, and the magnetic field it's going to be mu naught N into I, which is going to be produced magnetic field. So that means we can write it as mu naught N into I capital N is mu naught N into I capital N, where small n represents what? Small n represents number of turns divided by length. So now let us substitute. Divided by I is here. So then if you substitute here, L is equal to mu naught. N can be written as what? Capital N. I is going to be I. And again N is there. We can write it as N square. And mu naught will be there, n is there, I will be there, and here area we have to write. So then area will be here and divided by I get cancels. Then mu naught capital N square into A. So here n, small n is going to be having capital N divided by L will be there. So we have to include L also, because small n is equal to capital N divided by L. So that means mu naught n square A divided by L will be there. This is going to be the self-inductance coefficient for solenoid. And on what factors the self-inductance coefficient of a solenoid will depends. So it will be mu naught capital N cross section area A, and the length of the conductor is going to be conductor in the sense solenoid length is going to be L. So these are all the factors on which the induced EMF or self-inductance will be dependent. Self-inductance coefficient will be dependent. And one more thing, if in this solenoid a material is filled, for example a certain material, ferromagnetic material is filled, means definitely this material will having a permeability of mu, relative permeability for this material is going to be mu r is there, means, so we can write it as, so the induced self-inductance coefficient can be written as mu naught mu r capital N square A divided by L. So that means by seeing this expression we can say this is going to be the self-inductance, where mu naught mu r, so this depends on what factors, means depends on the medium, because relative permeability is there. That relative permeability is depending on the medium. It will vary with respect to the medium. More the relative permeability, more the self-inductance coefficient. So that means N represents the number of turns in the coil, and then area depends on area, length. So these are all the factors on which the self-inductance coefficient will be dependent. So next we will discuss, this is, you can assume it as a question also, you can also take it as a derivation also. Next we will discuss on a coil is there, a single coil. We will just take question. You are having a single coil, number of turns is going to be, you can imagine there were n number of turns will be there. So n number of turns, there were n number of turns will be there. So in this we are supplied a current of I. Now we are going to calculate what is going to be the induced self-inductance coefficient in this coil. So at the center we will calculate. So we supplied a current I. So for this we are going to calculate the self-inductance coefficient. What is the formula to calculate the self-inductance coefficient? L is equal to 5 divided by I. Now flux is going to be how much it is producing. So we can write BA, N is going to be the flux produced. Okay, so now this is going to be the current which is supplied. Now let us take, this is produces a magnetic field B, and cross section area of this is going to be A, and the number of turns is going to be N number of turns. Now we have to write what is the magnetic field produced by this. So we can write mu naught I divided by 2 into radius is going to be, so 2 into, let us take, this is having a radius r. Okay, so mu naught I divided by 2 into r is going to be the magnetic field produced by this coil. Now here mu naught I divided by 2r is going to be the magnetic field produced, but here how many turns are there, depending on that the magnetic field is also produces. That means let us multiply it by N. So this is the expression for magnetic field produced in the coil. Now we will write in this expression. Now if you write in this expression, magnetic field is going to be mu naught I n divided by 2r into I, and then here it is going to be again, here again it is going to be area is there. Let us take this area, and then number of turns will be there. So then we can write I get cancels. Then the expression is going to be mu naught n square a divided by 2r. So next what we will do, so here, so we will consider, so this is going to be the, we have to consider that here n is going to be the, capital N is going to be the number of turns. So now area, can we write it as in terms of mu naught n square, area can be written as pi into r square, because this is a circular loop, right? That means we can write it as divided by 2r. 2r, r square will get cancels, then it is going to be mu naught n square pi divided by 2. This is going to be the, so the self-inductance coefficient. This is going to be self-inductance coefficient. This is going to be the self-inductance. If you assume that this radius is going to be very small, only this equation is going to be valid. But J level though it is enough. You need not to worry about this. We assume that the entire in this region the magnetic field is going to be constant. By assuming that, so B is constant in the region, in the entire coil, okay. So then only this approximation will works. Otherwise uniform magnetic field won't be there, because at the center only the magnetic field will be there, but every point will not be having the same magnetic field. But we can say that an approximation that at the center as well as in the entire surrounding, if the radius is very small, means we can approximate that this is going to be the self-inductance. For J level this is enough. J level as well as KCT also you can write the same equations. Now once we understand the self-inductance question, so now we are going to understand about the mutual inductance. So let us talk with mutual inductance. Mutual inductance. So let's start with the mutual inductance. First I will take the definition. Mutual induction definition. Mutual induction is a phenomena. Mutual induction is a phenomena in which a changing current in one coil induces an EMF in a nearby second coil. This is called mutual induction. So what is mutual induction means? So let us say with an example. So statement is this: we have to consider mutual induction means two coils should be there. Mutual means one will produces the magnetic field, that magnetic field will link with the another coil, and then that will induces the EMF. That is called mutual inductance. Let us talk about the mutual inductance. So let us consider this is going to be in one coil. First coil we called, or primary coil we called This is the first coil. The first coil is having number of turns is going to be N1. The magnetic field produced by the first coil is B1, and the area of cross section is going to be A1 we take, and then flux produced by the magnetic flux produced by the first coil is going to be phi1, and this is going to be we have to consider, and the length also we have to consider. The length of this coil is going to be L1. Now what I will do, so this is the current flowing, I is the current flowing. Now I am going to keep another coil. This is going to be very near only, not very far distance. So this is going to be another coil. When you keep another coil, what will happen? So the magnetic field produced by this coil, the magnetic field produced by this coil will link with the second coil. So let us define the second coil. The second coil having the number of turns is going to be N2, B2, A2, phi2, and the length is going to be L2. So the length is going to be L2. Now what will happen? Actual mutual inductance means the magnetic field produced by the first coil will link with the second coil. When there is a changing magnetic field linking with the second coil means in the second coil there will be an EMF will be induces. So that induced EMF will be called as mutual induction. So that will induce us the EMF. That induces of induction of EMF in the secondary coil or second coil is going to be called as mutual inductance. So the current flowing direction will be opposite. That means opposes the change. On that direction only current will be flowing. So that means this magnetic field will link with the second coil and it will induce us the EMF. Now let us talk on what factors the EMF will be induces. So if is going to be current I1 is flowing here and the induced current is going to be, let us take this is going to be I2 is the induced current. Now this is going to be the actual meaning of the mutual inductance. In mutual inductance what will happen? It's going to be a phenomenon in which changing current in one coil induces an EMF in the nearby second coil. So this phenomena, changing current will induces the magnetic field, changing magnetic field will link with the secondary coil. That secondary coil changing flux will induces the EMF in the same coil. That means in this coil only the EMF will be induces. The secondary coil only the EMF will be induces. So this is going to be called mutual inductance. Now we will calculate. The first case is going to be if I1 is the current flowing in the first coil, so then the magnetic field produced will be B1. So that means magnetic field produced by the I1 is the current flowing in the first coil will produce us the magnetic field by the first coil is going to be B1, and the flux which is going to be linking with the second coil is going to be given as phi2. Remember this, phi2 is going to be the magnetic flux linking with the second coil. Now if you write this, we can write the direct relation. The relation is going to be I1 is proportional to the magnetic flux linking with the second coil. Remember this, I1 is proportional to the magnetic field produced by the primary coil, and this primary coil magnetic field or first coil magnetic field will link with the second coil. Okay, the flux which is producing in the second coil will be because of the primary coil magnetic field. That means I1 is the current flowing will produce the magnetic field B1 which will be responsible for the flux in the secondary coil. Now we will do the relation I1 is proportional to phi2. Phi2 is the flux which is linked with this secondary coil. Flux which is linked with the secondary coil. Now to remove this proportionality we will include a constant. So let us assume I1 is proportional to phi2. Now we will remove this proportionality means we have to include a constant that's going to be m, So is equal to 5 2. So there your M is going to be called as mutual inductance, mutual inductance, mutual inductance, mutual inductance coefficient, mutual inductance coefficient. So then we can write it as M is equal to phi 2 divided by I1. M is equal to phi 2 divided by I1. So remember, I1 is the current in the first coil, phi 2 is the flux in the second coil. Okay, this is going to be the mutual inductance. Now the second case in this, I am going to apply the time varying current here. So definitely time varying current will produce a time varying magnetic field. Ion is the current flowing in the primary coil or first coil, and the magnetic field produced by the first coil is a function of time, and the flux linked with the second coil is going to be given by as a function of magnetic field is a function of time by the first coil into the area of the second coil, and then number of turns in the second coil, not the first coil. Okay, so now this you have to know. Now in the form of equation you want to write means, so I1 capital M is equal to phi 1. So this is going to be the equation. So this is going to be the phi 2, sorry, this is going to be the phi 2, flux linked with the second coil, flux linked with the second coil. Now what we will do, we will differentiate this first. So if we differentiate this, M di1 divided by dt is equal to d phi 2 divided by dt. So that means here we can write it as M is going to be induced, this is going to be give you the d phi by dt is nothing but the induced EMF in the second coil, induced EMF in the second coil. It will be always opposes the EMF induced in the primary coil, means we have to write minus. So induced EMF in the secondary coil is can be M into di1 by dt. So minus is going to be the symbol. So because why we use the minus means it will be the induced current will be in the opposite direction, which will opposes the change in magnetic field, because you assume that the I is increasing. That means I is increasing means I current, the magnetic field is also increasing. To oppose this, it will produces the magnetic field in the opposite direction. It is going to be induces the current in the opposite direction. That's why we are taking here minus. This is going to be the induced EMF in the second coil. Okay, here M is going to be the mutual inductance. The unit for mutual inductance is, unit of mutual inductance is same as the self inductance unit, same as the self inductance unit. Okay, both are having the same unit. Now you can also answer directly, volt second divided by ampere, this is the unit. Okay, dimension formula you write on yourself, because voltage anyhow you know, second means time, ampere is the current. So this you can write in yourself. Now this is going to be the mutual inductance. Now for the solenoid we are going to do, so that you can assume it is a question. So let us take, there are two solenoids. So this is going to be a one solenoid, and another solenoid is overlap with the same solenoid like this. So this is going to be overlap, means there is no physical contact, all are insulated wires, they are going to be here like this, they are overlapped. Now here in the primary coil we will supply the current I as a function of time. Now in the secondary coil definitely there is an induced current will be there, which will opposes this direction. So that means this is the direction of induced current. Now we have to find out what is going to be the mutual inductance. Let us assume. So the mutual inductance in the coil we can calculate it as, So assume that the primary or first coil is having number of turns are N1 and the cross section area is A1 and the magnetic field produced is phi1, magnetic flux is going to be B1 and the length of the coil is going to be L. Assume that both are going to be having the same length. Now if you talk about the second coil having the number of turns as 2, N2, and the cross section area is going to be A2, and the magnetic field induced will be, it's not required but still we write, induced magnetic field will be B2, and then flux is going to be phi2, and the length will be L. Now what is the formula to calculate the mutual inductance? Mutual inductance is given by, so M is equal to the flux which is linked with the second coil divided by the current in the primary coil or first coil. So now flux linked with this, let us take I1 is the current flowing here and I2 is the current, induced current will be in the second coil. Now phi2 divided by I1. So now what we can write phi2? Phi2 is nothing but the flux. The flux can be written as N into B into A divided by I1 is the current flowing. So now you can easily answer, this is going to be the flux in the secondary coil. Secondary coil is having N2 is the number of turns and magnetic field from which coil we have to consider? From the primary coil we have to consider. So B1 is the primary coil magnetic field produced and A is going to be the area of which coil? Area of the secondary coil. That means it is the area of the secondary coil. Okay. So area of the secondary coil. This is going to be the flux value. And remember, what to consider is very, very important. In whenever a flux phi2 if you are taking, that means flux which is linked to the secondary coil we have to take. Flux linked to the secondary coil we have to take. Flux linked to the secondary coil means what? Magnetic field produced by the first coil, this is B1, and the area of what coil? Secondary coil. And then number of turns of which coil? Number of turns of secondary coil only we have to consider. And divided by the current, I1 is the current flowing in the coil. So this, where is the current? This is the current coil, current flowing in the first coil. So this is going to be the equation. Now we can easily answer. N2 is going to be remain same. So we will write N2 as N2 only. B1 is going to be how much? B1 is going to be the magnetic field from the primary coil. What is the expression? Mu naught N and the current in the primary coil and multiplied by A2 divided by I1. So let us take I1 get cancels. Now mu naught N can be written as what? N is going to be the number of turns in the primary coil or first coil divided by the length of the coil. So then if you do that, so then we will get N2 mu naught N is equal to capital N1, so A2 divided by L. So this is going to be the so the mutual inductance in the solenoid. So we can write mu naught A2 N1 N2 divided by L, and this is going to be the expression. Okay, so then area we can write it as another form you want to write, means in terms of radius also we can write pi r square is going to be, we can write, but coil, right, this is having some area is going to be pi r2 square we can say. So but that's not required. If you want to write you can write, but that is enough. This is enough, right? I think this is enough, you can write. So A2 is represents the area in the second coil, a second coil. So next we will do one more question, so which is going to be two rings are there. So let's take this as a question. So this is one ring and this is another ring, where in the first ring time varying current is flowing. Let us take I1 is the current which is flowing in the first ring. That means this is the first ring we will call. And in the second ring there is no current flowing. So but I is going to be varying with respect to the function of time. Let us assume R1 is the radius of the first coil or inner coil and R2 is the radius of the outer coil. So then we will take this also I2 also. Okay, this is a current flowing, because I is the current flowing. We don't want I inside also. We just need an I is the current flowing in the outer coil. Now what we have to find out is, what is the mutual inductance? If it is current is varying, definitely there will be a magnetic field is varying at the center. So you should imagine that R1 is very small than the R2. So then only we can do this. Now we can see what is going to be the formula for mutual inductance. Now we have to calculate the mutual inductance for this. So mutual inductance formula is equal to magnetic flux linked with the second coil divided by magnetic flux linked with the second coil divided by the current flowing in the primary coil. What is the magnetic flux linked with the second coil? If you assume here it is going to be N2, or we can say N number of turns are there means, so let us talk, this is an N2 and this is going to be the N2, N1, N2, okay. Number of turns is going to be N1 here and number of turns is going to be N2 here. So now flux we want to write means, it is very simple, NBA. So NBA means, so we can write magnetic flux will be linked to the secondary coil, or it is going to be, it will be confusing if I write phi 2. So then what I will do, so just we consider according to this expression, this number of turns also I will take it as 2, this I will take it as N1, and this also I will take it as R2, this I will consider as R1. Okay, so now we can say I1 is the current flowing here. Now we have to calculate the flux which is going to be linking with this coil. Now what is the flux linked with this coil? We can easily say it is nothing but number of turns in the second coil into V in the from the first coil into area in the second coil. Area in the second coil. This is the area in the second coil. Magnetic field produced by the first coil, and N2 is the number of turns in the second coil. So divided by I1 current. Now can you tell me what is the magnetic field produced by this first coil? The magnetic field produced by the first coil we can write as mu naught I1 divided by mu naught I1 divided by 2 into R is going to be the radius, which is the R here. R1 is the radius. This is going to be the magnetic field, because here N1 is going to be the number of turns are there means we can write, so it's going to be N1 turns also we have to include mu naught I1 N1 into 2R1. If you substitute here, N2 is here, mu naught will be here, I1 will be there, N1 will be there, A2 will be there, divided by I1 will be there. So this is going to be the I1 will get cancels. So now what we will get? So we will get N2 N1 mu naught into A2, mu naught into A2. So mu naught into A2. Okay. So this is going to be the expression for mutual inductance in the coil. Expression for mutual inductance in the coil. And here we need to understand that 2R1 is also there, right? So then we have to include that also. Mu naught I1 N1 2R1 is also present. So then if you include that, so 2R1, so we'll be giving you the mutual inductance in the coil. So that means mu naught N1 N2 A2 area of the second coil divided by 2 into R1. This is the expression. So many questions will be asking to find out the mutual inductance. In the exam also they will ask. So next, one more question we will discuss. Find the mutual inductance. If the mutual inductance, find the mutual inductance. Second question. Find the mutual inductance. Find the mutual inductance. Mutual inductance. Find the mutual inductance. Suppose you are having a square shaped coil. Each sides are going to be L, 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 L. Okay. So now at the center again one more square shaped, a very tiny square shaped, which is having a length of tiny, we can say, which is having a length of, so let us assume, okay, we will assume this is a length is going to be, this is A and this is B, this is B, and B is very smaller than A. Side length I am saying talking. So B is very smaller than A. Now what we have to do is we have to find out the what is the mutual inductance on the second coil. Let's call this is first coil, this is second coil. On the second coil from the first coil, so we are going to find out. So let us talk, this is first coil and the second coil. Now how to do this? So we know that magnetic field produced by a single rod. What is the expression? So the expression is going to be at any point the center we are going to take, and from here to here, this is going to be A is there, means it is easily you can answer from here to here, from here to here, and you can take here, it's going to be here to here, so you can be here to here and then here to here. All these sides are going to be having the length L. Now we can say from here to here. So now we have to find out this point, what is this distance. We know that A by 2 here, and this is going to be definitely, it's going to be having, so root 2 A will be there, root 2 A divided by 2. How I consider? So because in the diagonal length is going to be, it's going to be root 2 into A. Pythagoras theorem if you apply, you will get root 2 A, but half of the diagonal means we will get root 2 A divided by 2. Now what we will do, by after considering this, so we can easily find out this length. So this length is nothing but, we know that this is A and this is going to be A by 2 means, so this is going to be what? This is going to be definitely we will get around 45 degree we will get, because this is a square. So 45 degree means this side is can be easily answered. So this is going to be cos root 2 A by 2 cos 45 degree. What is cos 45 degree means? 1 by root 2. So root 2 A divided by 2, cos 45 is nothing but 1 by root 2. 1 by root 2 means root 2 get cancels, then we can write it as A divided by 2. A divided by 2. This is going to be the, so A divided by 2 is going to be the length of the A divided by 2 is going to be the length of this rod. Okay, this part of this going to be this is the length of this part of the, from center to the rod, the length is going to be A by 2. After getting the A by 2, we can easily find out the magnetic field. Which formula we have to apply? From the single rod, magnetic field can be at the center can be calculated as mu naught I divided by 4 pi into distance sine phi 1 plus sine phi 2, sine phi 1 plus sine phi 2. Okay, so sine phi 1 plus sine phi 2. Now we will substitute. Magnetic field produced by a single rod can be calculated as, so I1 is the current flowing here. So let us take I1 is the current flowing here. Mu naught I1 4 pi, D is going to be how much? A by 2 into sine phi 1 means what? Sine 45 degree. Sine 45 degree 45 degree plus sine 45 degree, then will give you 1 by root 2, 1 by root 2. It is nothing but magnetic field at the center. From the single rod we are calculating. For single rod we are calculating. Later we will multiply this. So then what we will do? So this is going to be mu naught I1 divided by 2 pi a, because 2 1s are 2 2s are. Sine 45 can be written as 2 root 2. So we will write sine 45 as 1 by root 2, 1 by root 2. So then we will add that, we will get 2 root 2. 2 get cancels. Then the magnetic field is going to be mu naught I1 divided by root 2 pi into a. This is the magnetic field. After getting the magnetic field, next what we have to do? Multiplied by 4, because how many are there rods? 1, 2, 3, 4. So this is going to be the 4 rods are there. That means in the center the magnetic field is going to be 4 into, for at center magnetic field is given by so we can write it as, at the center we can write it as net magnetic field is given by 4 into mu naught into I1 divided by root 2 pi into a. This is going to be the at the center magnetic field. Now what we will do? So now we will calculate what is going to be the mutual inductance. What is the mutual inductance formula? Magnetic field produced by this entire coils, 4 coils are there, 4 wires are there, or 4 sides are there. We calculated at the center what is the magnetic field. Now we are going to write what is going to be the mutual inductance. So flux linked with the second coil divided by current flowing in the first coil. So flux linked with the second coil can be written as what? Flux linked with the second coil can be written as BA, magnetic field from the first coil, and the area is going to be in the second coil, BA divided by I1 current. Okay, what is B here? So we can write B as 4 into mu naught I1 divided by root 2 pi a, and I1 is the current flowing, and here A2 is the area. Area, so easily we can write it is nothing but B square. So then I1 get cancels. So then we can write it as, so capital M is equal to mutual inductance is going to be 4 mu naught B square divided by root 2 pi into A. This is going to be the mutual inductance. So further you want to write means we can write it as 4 can be written as 2 into 2 and then mu naught B square divided by root 2 phi into A. Again 2 can be written as root 2 get cancels. Then we can write 2 root 2 mu naught B square divided by pi into A. So this is going to be the expression. Okay, this is going to be the mutual inductance value. You have to ready to answer this type of questions. Okay, so there is then another method to find out the mutual inductance. I am going to take you that method also. There is a relation, we can say there is a relation between mutual inductance and self-inductance. What is that relation? So the relation is going to be given by suppose you are having a two coils. So self-inductance for the first coil is L1 and the second coil is going to be L2. Now if you take mutual inductance between this coil means K into root of L1 L2, where K is called coupling constant. Coupling constant. So what is K means? K is called coupling constant. So where this is going to be the first coil and this is the second coil, the coupling constant can be given as K is equal to magnetic flux in the second coil and the magnetic flux in the primary coil. So that means magnetic flux linked with secondary coil. This is a unitless constant, we should remember. If you are calculating the mutual inductance by self-inductance method, then magnetic flux linked with the second coil and magnetic flux linked with primary coil. Magnetic flux linked with first coil. Okay, so this is going to be called. So one more method to calculate the mutual inductance. So by knowing the self-inductance value only. But K value, when it is going to be more, when it is going to be least, that is very important. So that means, what is the meaning actually? How much flux linked with the second coil will be given by this coupling constant. For example, you are having a coil, let us take one coil is going to be like this and another coil is going to be like this. Then the coupling constant between them is going to be, we can say K is equal to exactly 1, because all the magnetic field produced by the first coil will link with the second coil. That's why coupling constant will be 1. For example, you are having a one more coil is like this and another coil is going to be somewhere like this. Then there is no interaction of magnetic field from the first coil and the second coil. So that means coupling constant will be 0. And one more is there. So we can say, so this is going to be the one more coil and this is going to be another coil. If you consider this, so both the coils are going to be perpendicular each other. Now again the coupling constant will be 0 because there is no magnetic flux link with the second coil. This is called coupling constant. Now, so the coupling constant, so we can also say, for example, you are having a one coil is like this and another coil is going to be somewhere near to like this. That means here we can say coupling constant will be varying from 0 to 1. Only in this case only it is possible. Okay, so coupling constant can be vary from 0 to 1. By seeing the coupling constant, there is no unit for coupling constant. Coupling constant is a unitless quantity. K is a unitless quantity. Okay, by knowing the unitless, that means coupling constant, we can determine the mutual inductance. This is another method of finding the mutual inductance. Now, on what factor the mutual inductance depends? By seeing the equations only you can answer. So just observe here. So mutual inductance, on what factors it will depend? So factors on which mutual inductance depends. The first factor is going to be medium inside, because medium is very important, because the relative permeability will come. Area of second coil, number of turns and length. All this, only these factors, does not depends on the current flowing. Okay, mutual inductance does not depend on the current flowing. Mutual inductance as well as self inductance does not depend on the current flowing in the circuit or in the coil. Okay, so now after understanding this, one more last topic is there, that is called energy stored in the inductor. Energy stored in the inductor. For example, you are having a inductor. This is an, remember, solenoid will also be called as inductor when the time varying magnetic field is, time varying current is supplied. Please remember, same coil will be called as solenoid if it is producing only constant magnetic field. Now the same coil is time varying current is supplied, means it is going to be called as an inductor. Now for this inductor, now we are going to talk about the what's going to be the energy stored. How do you write the energy stored? Energy stored can be written as, we know that induced EMF is going to be minus L di by dt. This is the induced EMF in the coil. So that means we know that power can be written as V into I, where we can write it as power is nothing but, so total energy per unit to time, total energy in the inductor per unit to time. V is nothing but potential which is going to be developed. Need not to take the minus here because it's just show the opposite direction. Now you say L di by dt into I. Now what we can write, dt get cancels. Now total energy stored in a given time interval we have to calculate as integrate on both the sides. Then L into I into di can be written as, so from here to here if you take, so then E is equal to L into I square divided by 2. So that means half into L into I square. This is the energy stored in the inductor in the form of magnetic field. Okay, so and one more thing very important, the unit of self inductance or mutual inductance, the unit of self inductance or mutual inductance is also called Henry. Henry is the unit of self-inductance or mutual inductance. Remember this, 1 Henry is equal to volt. So we can write 1 Henry is equal to, so we can write 1 Weber per ampere. 1 Weber per ampere, or we can also write